In today's video, we're going to discuss how probability generating functions can be used to find probabilities of a distribution. This is the second video in applications of probability generating functions. So let's formalize how they can actually be used to derive probabilities. For a discrete random variable x with PGF or probability generating function capital Px of z, the probability Pxn, this is a lowercase p, which we're going to define as the probability x is equal to n, can be evaluated by taking 1 on n factorial times the nth derivative. Let me make that a bit more clear. The nth derivative of the probability generating function evaluated at 0. And in case that definition isn't clear, I'm going to write 1 on n factorial of dn on dzn of the probability generating function evaluated at z is equal to 0. Now, I want to prove this fact with some certainty and some rigor. So, to do that, I'm actually going to start with the left-hand or the right-hand side of this equation. So, we've already discussed the right-hand side is 1 on n factorial px, the nth derivative, evaluated at 0, which we've already discussed, is the 1 on n factorial dn on dz to the n, probability generating function evaluated at z equals 0. Now, I'm going to use our definition of the probability generating function to replace Px of z instead with the polynomial definition Pn. That we recall we defined the probability generating function as the sum of x equals 0 to infinity of z to the x multiplied by the respective probability mass function. And again, we're still evaluating 0. In this step, what we recognize is that we're dealing with a derivative of a sum of functions. Now recall that if you take the derivative, say, of a series of functions, say f of z plus g of z, if you were to take the derivative of the sum of two functions of z, this gives you their respective derivatives, or the sum of their respective derivatives. In a similar fashion, if you're to take the nth derivative of the sum of functions, that is also going to give you the sum of the nth derivative of the respective functions. So keeping that in mind here, where we have dn, or the nth derivative with respect to z, of a sum of functions in z, we can rewrite this as 1 on n factorial sum x equals 0 to infinity of dn over dzn times the functions themselves. Z is equal to 0. Again, notice here that we're dealing with a derivative with respect to the variable z, but we have a component here which is independent of z, or constant actually with respect to z. Now recall that if you take the derivative of, say, alpha, which is going to be a constant, right? If this is constant, at least with respect to z, then this derivative becomes alpha times the function, the derivative of the function. And in a similar way, if you were to take the nth derivative, dn on dz to the n of alpha f of z, this becomes alpha times the nth derivative of the function. Keeping that in mind, this is a constant with respect to z, so we can actually bring it outside the front of the derivative. So this becomes 1 on n factorial x equals 0 to infinity of px of x multiplied by the nth derivative of the probability, of not the probability mass function of z to the power of x. And again, we're evaluating at z is equal to 0. Now, we want to come up with an expression for the derivative of z to the x. So I'm going to do that on the side here. The derivative, or the nth derivative of z to the x, we can think of this as first taking the derivative of z to the x, but then taking dn minus 1 dz n minus 1, n minus 1 more derivatives after taking one derivative. Now, if we take the first derivative here, what we get is xz to the x minus 1. This is because of the power rule. This is a polynomial in z. Because it's a polynomial, we bring the power down the front x, and we've got x minus 1 here. And of course, we're still dn minus 1 on dz to the n minus 1. We're still taking the nth derivative, the n minus 1th derivative. Now, taking the n minus 1th derivative is the equivalent of taking the first derivative, xz of the function, and taking the n minus 2th derivative at the start. Now, if we were to evaluate this expression, again, this is a polynomial in z. We bring the power down the front, 1 off the power. So this still becomes dn minus 2 on dz n minus 2 of x minus 1 z to the x minus 2. Now, we notice a pattern here. First, we brought down an x. Then we brought down an x minus 1. Next, we'll bring down an x minus 2, then an x minus 3, and an x minus 4, and so on and so forth. And we also notice that our power goes from x, then it goes to x minus 1, then it goes to x minus 2. That's at least after 2 derivatives. So, after n derivatives, if we were to do it all in one, this would leave us with x minus 1, x minus 2, ... all the way to x minus n plus 1, and our power would be z to the x minus n. This is just continuing on from the recognized pattern that we saw above. Now we can substitute this expression in to the expression that we had above. So this becomes 1 on n factorial times the sum x equals 0 to infinity of the probability mass function times, it was x minus 1, x minus 2, ... x minus n plus 1, z to the power of x minus n, and again we're evaluating at z is equal to 0. Now here's an interesting point to note. Look at the first terminal, it's 0. What happens when I substitute in 0 into this expression here? Well, I'm actually going to notice that this first term, this x term, will become 0, and therefore this is a product, and we're multiplying by 0, and therefore the whole product becomes 0. Interesting. What about the next terminal? Because we're going to go from x equals 0, then x equals 1. Well, when x equals 1, this term here becomes 0, and therefore the whole product becomes 0. When x equals 2, this term becomes 0, and therefore the whole product comes equal 0. All the way up to where x equals n minus 1. These terms all become 0. And therefore, we don't need to go from x equals 0. We can actually start this whole expression rather at x equals n to infinity, because x equals n is the first time in which this expression is non-zero. So we go, and then we go px of x times x minus 1, x minus 2, dot, 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 x minus n plus 1, z to the x minus n. And again, we're evaluating it, z is equal to 0. Now, what I'm going to do next is I'm going to break this term up into two parts. The first part is when x equals n, and the next part is when x equals n plus 1 and above. So doing that, we get 1 on n factorial. The first time is evaluated by pxn multiplied by n minus 1 dot 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 multiplied by n minus n plus 1 z to the n minus n. That is the first term. Simply substituting in the first terminal into this expression here. The next part of this summation, of course, we can rewrite as n equals 1 to infinity of px of x times x minus 1 dot 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 x minus n plus 1 z to the power of x minus n, of course evaluated at z equals 0. Now, here's the interesting part. This 1 on n factorial can stay the same. We've got a px, we've got a px to the n, so that stays the same, pxn, times, okay, we've got an n, times, what else do we have? We have an n minus 1 times dot 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 dot, times how far do we go? Well, look, we go all the way to n minus n plus 1. In other words, we go all the way to 1. And then what's another thing we recognize in the simplification? The z to the n minus n, that collapses to z to the 0, and anything to the power of 0 is 1. So we also get a times 1 here. And of course, here is the next part. The next part is to recognize that when z is equal to 0, we're looking at this summation now. When z is equal to 0, 0 to the power of anything is 0. And therefore, this entire expression becomes, sorry, I forgot to rewrite this integral as x equals n plus 1. Sorry, I made that mistake there. This entire expression here becomes z is equal, well, z equals 0. The whole expression becomes 0. I can just write plus 0. And therefore, finally, in our expansion here, we get 1 on n factorial times px of n times, by definition, n times n plus 1 times dot 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 all the way to 1 is also n factorial. And then we notice that this n factorial cancels with this n factorial, and we're left with px of n, or in other words, the probability x is equal to n. And there you have it. We've proven this fact here that the probability x equals n is 1 on n factorial times the nth derivative of the PGF evaluated at 0. Let's solidify this understanding with an example. Here is our example above. Let x be a PGF, or let x be a random variable with a probability generating function given by the following. You might recognize that PGF from the previous video, but for now, let's say we're just given the PGF at face value. We're asked to find the probability mass function of x. Well, the first thing we need to do is evaluate the derivatives. So px, the first derivative of the probability generating function with respect to z, remember, is by definition the derivative of the PGF, which in this case is d on dz of 1 out of 5, 1 plus z squared plus z cubed plus z4, close the brackets. In this particular instance, like I said before, the factor when you have a derivative of a constant times a function of z, the constant can just come out the front of the derivative. So we've got 1 out of 5. And then we can, of course, differentiate the expression inside here. When we do differentiate the expression inside, we're left with the derivative of 1. Apologies, I have forgotten a term here. 1 plus z squared. Please correct that in your question. And here, this should be the derivative of plus z squared plus z cubed plus z to the 4. Good. Now that we've done that, we can evaluate the derivative. Same principles apply, except now the derivative of 1 is just 0. The derivative of z is 1. The derivative of z squared is 2z. The derivative of 3, or z cubed, is 3z squared. And then, of course, the derivative of z to the 4 is 4z cubed. In a similar fashion, we can evaluate the second derivative of the function. That is just the derivative of the first derivative of the function. Then that becomes d on dz. Plug in our expression, 1 on 5, 1 plus 2z plus 3z squared plus 4z cubed. Again, we're taking a derivative of a constant times a function. The constant out the front can simply stay out the front. And then the derivative of these functions, well, the derivative of 1 becomes 0. The derivative of 2z becomes z. The derivative of 3z squared, the power comes down the front. So the 2 gets multiplied by the 3 to give you 6. And of course, the z squared here becomes 1 off the power z to the power of 1, or simply z. And then our expression here of 4z cubed, again, the power 3 comes down the front to give us 3 times 4, or 12. And then 1 off the power gives us 2 in the power instead of 3. Again, similarly, we can derive third derivative, which is the derivative of the second derivative, which in this case is d on dz of 1 out of 5, 2 plus 6z plus 12z squared. which in this case, again, the 1 out of 5 can come out as a factor. The derivative of 2 is simply 0. The derivative of 6z gives you 6. And then the derivative of 12z squared, the 2 comes down the front to give you 2 times 12, or plus 24. And then the z squared here, well, that simply collapses to simply z, 1 off the power. And finally, the last derivative here, or the fourth derivative with respect to z, is equal to the derivative of the third derivative with respect to z, which is d on dz of 1 out of 5, 6 plus 24z. In this particular instance, we've got the fifth comes out again as a common factor, or as not as a common factor, but the fifth comes out as a scalar. And then the derivative of this whole expression here is simply just 24. So we can say times 24, or in other words, 24 out of 5. If we were to take the fifth derivative, 1, 2, 3, 4, 5 of z, this would be the derivative of the fourth derivative, right? 1, 2, 3, 4 z, which in this case d on dz of, well, it's a constant, 24 on 5, which is 0. And in fact, if we were to take the nth derivative of z, that would equal 0, where n is greater than or equal to 5. Because when we keep on differentiating 0, we end up with 0. So we've found our derivatives here. Using these derivatives, we can now find the probability mass function. Now recall that the probability mass function at n is 1 on n factorial times the nth derivative evaluated at 0. Keeping that in mind, we can now evaluate px of 0. Px of 0 would be 1 on 0 factorial px, the 0th derivative evaluated at 0. Now, 0 factorial is simply equal to 1, so it becomes 1 on 1 out the front, times. Now, the 0th derivative of a function, which is a funny way of saying it, but the 0th derivative is just the function itself. That's what we mean by the 0th derivative. So it's just the function evaluated at 0. This becomes 1 on 1 times. Now, our function was 1 on 5. And we actually had it up here. Here was the function 151 plus z squared plus z cubed plus z to the 4. So it becomes 1 on 5, 1 plus 0 squared plus 0 cubed plus 0 to the 4, which is simply equal to 1 on 5. Px of 1 is equal to, in this particular case, 1 on 1 factorial times the first derivative of x evaluated at 0, which is now 1 factorial is just equal to 1. So again, it's 1 on 1 times, I'm going to rewrite the first derivative as p1 dash p prime of 0, which in this case is 1 on 1 times 1 on 5. Where was the expression we had before for the first derivative? It was all the way up here. So using that expression above, and hopefully I can have both in the same, maybe both on the same page, just if I zoom out far enough, that becomes 1 on 5, 1 plus 2 times 0 plus 3 times 0 squared plus 4 times 0 cubed. And after evaluating that whole expression there, it just becomes 1/5. The next probability is probability of x equaling 2, which is 1 on 2 factorial, the second derivative evaluated at 0. Now 2 factorial that we have here is simply equal to 2. I'm going to rewrite the second derivative with double prime at 0, which is equal to 1 on 2 times 1 on 5. We had our expression above. Where was it? Here it was. It was all the way up here. So that becomes, again, I'm going to try and get them both in the same page. Becomes 152 plus 6 times 0 plus 12 times 0 squared, which, what do you know? When you evaluate this, these terms drop to 0. This becomes 2, therefore, and that cancels with the half, leaving us with 1/5 as well. We're going to do the same for 3. Px of 3, or the probability x equals 3, is 1 on 3 factorial. Px of 3, or the third derivative times the third derivative. Now, 3 factorial is equal to 3 times 2 times 1, which is equal to 1 on 6. The third derivative I'm going to rewrite as triple prime evaluated at 0. That becomes 1 on 6 times 1 on 5. Again, we want to come up with our expression. Where was it? Here. Here is the triple derivative up the top here, 6 plus 24z. So it becomes 6 plus 24 times 0, which is equal to, well, in this case, this expression, 24 times 0 is just 0. We're left with 6. It cancels with the 1 on 6 at the front, which leaves us, therefore, with the 1 on 5. So that becomes 1 on 5 as well. Px of 4 is equal to, by definition, 1 on 4 factorial. Px, the fourth derivative evaluated at 0. Now, 4 factorial is 1 times 2 times 3 times 4, which is 24. I'm going to rewrite this as quadruple prime evaluated at 0. This becomes 1 on 24 times 1 on 5. Here was the fourth derivative. It was simply 24 on 5. So let me rewrite that as 24 on 5, which is just simply equal to 1 on 5. And if we were to take Px of n for n greater than or equal to 5, it would be simply equal to 0. Why? Because the nth derivative, or the nth derivative, evaluated to 0 when n is greater than or equal to 5. And therefore, we've found our probability mass function. It is actually equal to, in summary, Px of n is equal to 1/5, or n equals 0, 1, 2, 3, and 4. You'll notice that all the probabilities are 1/5. And hey, if you add up 1/5 plus 1/5 plus 1/5 plus 1/5 all the way to the end, you get 1. So it is, in fact, a probability mass function by definition. As you can see, it was quite computationally intensive to derive the probabilities using the PGF, and so typically we stick to using the PMF. Nonetheless, we have shown that it is in fact the case that you can use the probability generating function to derive the probabilities. I hope this video was useful. Thanks for watching. Hope to see you in the next one.